Hello and welcome. In this video, we're going to take a look at rational expressions. And you can think of them basically like a fraction, except that in the numerator and the denominator, we have polynomials. So, multiplication, division, addition, and subtraction kind of work like you'd expect, except that things are a little bit more challenging to simplify. You're going to have to probably use a lot more factoring. So we'll start off with some of the basic concepts. I'll give you a couple examples about how to multiply, divide, and add them, and then we can do some more examples in class. So let's take a look at the notes. So like I say, the definition of a rational expression is a fraction. It's got a polynomial over a polynomial. And again, a polynomial could have two terms, in which case it'd be a binomial. It could have three terms, it could be a trinomial, but it can have as many terms as you want, hence the idea of a polynomial. Now, if you start including square roots and stuff in there, technically it's called a fractional expression. I often make the mistake of calling them a rational expression as well. Just think about a rational expression is really a fraction with polynomials. Now, one of the first things that's going to happen is when you have a polynomial in the denominator, you're going to have to make sure that you don't use values for any variables that result in 0 in the denominator. When we talk about the domain of some expression or function, then we're going to be looking at what numbers the variables are permitted to have. So first of all, just to talk about domain before we start actually concerning ourselves with how to take multiple rational expressions and combine them, just think about what values the variables are permitted to have. Now here I'm saying variables, but oftentimes we're going to be using single variable expressions. So oftentimes there's going to be a single x or maybe a single t or s or whatever symbol. So if you just have a basic expression that's a rational expression, it could be just as easy as 1, which is about the most boring polynomial you can come up with, over x minus 2, which is a pretty boring polynomial. It's linear, it's not even quadratic, it doesn't even have an x squared. But it's pretty simple right away to think about what values would end up being not permitted. What would cause the denominator to equal 0, resulting in 1 divided by 0? Well, in this case, we're not permitted to have x minus 2 equal to 0. Not permitted. So if you wanted to, you could treat that as an equal 0 and say this is what we're not permitted. You could also cross that out and say x minus 2 cannot equal 0. Whichever way, solving for x is pretty easy by adding 2 to both sides. X cannot equal 2. This is where it's helpful to look at the real number line and think about what numbers are not 2. Well, here's 2. What numbers are not 2? Well, it's everything else. That means I can shade in all the numbers to the left and all the numbers to the right, leaving myself with a whole at 2. And so because I've got these two segments of the number line, I can write this out in interval notation. Now the first segment here doesn't seem to have a starting point. It goes all the way to the left. What's the lowest real number? Well, there isn't one. It essentially goes infinite in both directions, so we write down negative infinity as kind of our starting point and going up to 2. Now, 2 is not included, and infinity is not an actual number. It's not a thing that we stop at. So we use a round bracket anytime you involve negative or positive infinity. Now, the second line segment starts at 2 and goes off in the positive direction to positive infinity, but we're not including 2 in the domain, but x could equal 2.01 is fine. And we're going to go all the way up to infinity, but that doesn't mean we're stopping anywhere. It continues on forever, so we always use a round bracket for infinity. And the set of real numbers that x can be would be anything in negative infinity to 2, or, so union, 2 to infinity. That's our domain. Now they do get a little bit trickier in some circumstances. Okay, here's another basic rational expression, and I'm just using 1 again for the numerator. You could have something much more complicated than numerator, but it won't affect the domain. The domain is always just kind of looking about the denominator when you're talking about rational expressions. The only thing that we're really concerned about with here is when does the denominator equal 0, and those are the values we're not permitted. So essentially, denominator cannot equal 0. And we can write that down immediately as an equation. X squared minus 5x plus 4 may not equal 0. Okay, now you try to think about what values x is not permitted to have, and then from there you have these holes on the real number line, and you can write out the rest of the values in interval notation. Now, in this case, we have a quadratic in the denominator, and luckily we know how to factor those. This is a leading coefficient of a 1, which makes it a little easier to try to guess two values that add to -5 and multiply to +4. Now, two numbers that multiply to a positive, meaning they are either both positive or both negative, but because they add to -5, they must both be negative. Try it out. Take a guess, check it, and see if you got it right. X minus 1, x minus 4. They both multiply to +4 and they add to -5x, so we're good. And we're treating this as these things cannot equal 0. But remember, you can just think about this. The values that we're not permitted to have for x is when it does equal 0. Now, if you ever have the circumstances where you have two factors here multiply to 0, this is called a 0 product because it's a product of multiple things that equals 0. The only way that you're going to have stuff times other stuff equal to 0, and I'm not using very technical terms here, but anytime you have multiple factors equal to 0, then either one of those factors is going to have to equal 0. There's really no way to have multiple things multiply together to equal 0 unless one or more of the factors equal 0. So you're going to take each of these individual things and say, okay, what if that's equal to 0? What does that mean x has to be? If that other stuff equals 0, okay, well, what does that mean x has to be? Now, use that same concept here. We're not allowed to have x minus 1 equal to 0. Otherwise, we'd have 0 times other stuff. And we're not allowed to have x minus 4 equal to 0. Otherwise, we'd have x minus 1 times 0, and that wouldn't be good either. The two values that we're not allowed to have x equal to would be 1 and 4. All right, that leaves two holes in the real number line. We've got 1 and we've got 4. So that leaves you with 3 line segments left for the real number line, from -infinity to 1, from 1 to 4, and from 4 to infinity, not including the 1s and the 4s, and certainly not including infinity as an actual number. Okay. Now we've kind of looked at the domain, and that's just the first step there. So every time you have some sort of rational expression, your first thing is maybe just looking at it and factoring it. That's actually going to help us with all of the other things we're about to look at. Factoring is key here. If you ever especially have a quadratic, chances are it's probably good to factor it. It helps you out with the domain, it helps you out with simplifying. So speaking of simplifying, and then we can look at multiplying, dividing, and adding. Let's get into that now. Okay, first up, looking at simplifying, and this is going to be a major use for factoring. Now, I've deliberately set this up so that we have a quadratic on the top and a quadratic on the bottom. Now, the quadratic on the top is a trinomial, so you're going to try to maybe use some guessing and checking as to how to factor it. I don't have to use the AC method in this case because the leading coefficient is a 1. So try to think of just two numbers where they add to 2 and multiply to -8. Of course, I've deliberately set this up to work. X plus 4, x minus 2. Now what about the bottom? That's not a trinomial, so trying to do this idea of guessing and checking so that the two numbers add up to the middle term, it might not be as intuitive because you don't see a middle term there. However, this is actually one of the special product formulas. We have a square minus a square. Also, just if you want to know that, we tend to call that a difference of squares. That's another way to call that. Square minus a square. And so we have a little special product formula for that. Square minus a square. That's actually when you have a plus b, a minus b. So in this case, x squared minus 2 squared can be factored into x minus 2, x plus 2, or x plus 2, x minus 2. Multiplication is commutative, so it doesn't matter which order you write the brackets in. Now you'll notice that if you have a common factor on the top and a common factor on the bottom, just the same way as we can cancel that in a fraction, we can cancel that in a rational expression as well. X minus 2 and x minus 2 are common factors that can be canceled out. So that leaves us with x plus 4 over x plus 2. Now a little note here, the original expression and the new expression are equivalent in most ways. Now you might want to think about what makes them not quite equivalent. Well, you see that I factored first, which is very useful for finding the domain. So right away here I can see from the two factors that x cannot equal 2 and x cannot equal -2. In this new expression, it seems like only one restriction remains. X cannot equal -2. So they're equivalent in most ways except for the domain. Okay, so obviously factoring is a big useful tool here for trying to simplify big rational expressions, but along the way, try not to forget that in many cases that will slightly change the domain from what you started with to what you have now. All right, now let's work on some basic operations. The more basic ones when you're talking about fractions are multiplying and dividing. So it's pretty much the same story here. If you have a rational expression, multiplication and division are much easier to work with. And simplifying is also still important all the way through the process by factoring and canceling common factors. Okay, as a reminder here, I've just written out the rules for multiplying and dividing fractions, except I'm using capital letters here, and the capital letters just imagine as being multiple polynomials. So A, B, C, and D could be whatever polynomials are typically involved in your rational expression. And there may be two different ways that you see division written. You can have a fraction divided by a fraction along a single line, or you might have a compound fraction where you have a fraction over a fraction. Now that means that the numerator and denominator of the big fraction are actually also fractions themselves. In this case, they'd be rational expressions. Now, along the way, instead of having to do a lot of distributing, it's actually better, usually when you're multiplying and dividing, to keep things factored. And if things are factored, then you can cancel common factors. Okay, here's a basic example of multiplying two rational expressions, and I'm using lots of quadratics, but the 2x plus 4 is not a quadratic, so that one doesn't have an x squared. That polynomial is linear because it only has an x as its highest power. Okay, now what I can do immediately is just start putting everything together. I can have numerator times numerator over denominator times denominator. But maybe it might be better to take a look at each individual rational expression, there's two of them, and see whether or not there are common factors that can cancel out now rather than later. That would mean some factoring, and you can try factoring x squared minus 1 because it's a difference of squares. You can try factoring x squared plus x minus 2. Use guessing and checking and see whether or not you can find two linear factors that might factor that quadratic. On the right-hand side, 2x plus 4, you might be able to find a common factor between those two terms. And the x squared plus 1, well, it's not a difference of squares, it's a sum of squares. And we don't have a special product formula for that. It's also not a trinomial, so we can't really use the trinomial techniques with that one. If you really try hard, you can always, have x squared plus 0x plus 1. That makes it a trinomial, but I don't think you're going to be able to find two numbers that make that factorable. So let's see what we get once we factor as much as possible. Okay, I've factored that as much as I can possibly factor it. And you notice that x squared plus 1 was just a polynomial that we couldn't seem to factor. That's okay, it's going to happen sometimes. And you'll see maybe some opportunity here to simplify. There is an x minus 1 common factor of the numerator and denominator of that first fraction, the first rational expression. That means I might as well cancel it out now. Now, we can multiply together, and it's always best to take things like the 2 and other coefficients and really just bring them out to the front because the order of multiplication does not matter. So the 2 can be written out front, times x plus 1 times x plus 2. And in the denominator, we have an x plus 2 times an x squared plus 1. Once again, look for opportunities to factor. Everything is now one single rational expression. There's a common factor of x plus 2, and I can cancel that out, leaving me with just 2 times x plus 1 over x squared plus 1. And I'm going to leave that factored because we aren't really doing anything else other than simplifying right now. If we need to, we can expand things back out and collect terms if we want. Now, division works much the same way. You just have to make sure that you take the reciprocal of the divisor, and then you can start trying to cancel things out in much the same way. But what about adding and subtracting? Well, I've just written out a couple of the major properties for adding fractions. Subtracting works the same way, so if you want to, I can also write that one out with subtracting. But the main idea here is you need to have a common denominator. Now, on the right-hand side, the other property I have here is how to create an equivalent fraction. A over b is equivalent to ac over bc. Just by adding any factor you like, you can multiply top and bottom, numerator and denominator, to get an equivalent fraction. So, whenever you don't see a common denominator, use the idea of multiplying additional factors onto the numerator and denominator so that you can get the common denominator that you need. It's not always easy to find the common denominator. Sometimes you actually need a factor first just to see what factors are missing from one rational expression compared to the other one. And here's a simple example where you can see that there's nothing to factor. Everything here is either a constant or a linear polynomial. There's no quadratics to factor. So they don't have a common denominator. I can't add them just yet. I need to look for some way to make sure that the denominators are the same. And if I take this 7 over x minus 2, I can always take the top and bottom and multiply by another factor, x plus 5. Now, using a times, like a cross symbol here, doesn't really help to distinguish between x's and multiplication. So a lot of times it's better to change that to a multiplication dot instead. Down at the bottom here, I'm going to take x minus 2 and pop another factor onto it by multiplying by x plus 5. And on the other fraction, well, I have an x plus 5, and I can add another factor on there, multiply a factor of x minus 2. Now that looks pretty messy there, so maybe it's just better to write this all out And once you've written it all out, you can see that the denominators are the same because the order of multiplication doesn't really matter. And now you have A over C plus B over C. Using the addition operation, that leaves you with A plus B all over C. You can choose which way you want to order those two factors in the denominator. All right, that's how you can add. Now, you might want to take that a few steps farther and see whether or not you can simplify. Now, to simplify is always about looking for common factors. It's really hard to find common factors when you actually have two groups of factors with nothing in common currently. So the first step, if you want to simplify, should usually be expanding things out and collecting terms. Collect like terms, 7x and 3x, 35 and minus 6. And then from there, see if you can factor it. I don't see any common factors between 10x and 29, so it looks like that's as far as we can go. However, remember that when you simplify, if you find a common factor with the numerator and denominator, then you can cancel them. What about if the denominator is a little bit more complicated? What if the denominators are maybe quadratics? Finding a common denominator of two quadratics might be a little bit easier if you are able to factor them first. Okay, now this example definitely looks like it's a level of difficulty higher. There's a couple quadratics involved, and if you wanted to find a common denominator, you could go ahead and just take a quadratic and multiply it by the other quadratic and get a common denominator. It would just be as easy as taking the two denominators multiplied together. But if you end up going with a common denominator that might be that big, that complicated, chances are you're going to be spending a lot more of your time trying to simplify. But right now, you might actually have a much better time factoring and looking for a simpler common denominator. So let's begin by factoring each of these. Now I've made this this first trinomial have a leading coefficient of a 3, which might make you think, oh no, I have to use the AC method, and that is quite a long process. Now you could go ahead and try the AC method, but remember when we look at factoring, sort of the first strategy you might want to try thinking about is looking for a common factor. 3x squared, negative 3x, and negative 36 all have 3 in common. You can factor out a 3 or a negative 3, but I'm going to try to keep that leading coefficient positive, so I'm going to factor a 3 out. And that's super good news because that leaves us with a trinomial in brackets with a leading coefficient of 1, and that might be easier to factor further. What about the other quadratic? That is a trinomial as well, but it has a leading coefficient of 1. See if you can factor that. And that one seems to be factorable, x minus 4, x minus 4. And that was me just using some guessing and checking and looking for numbers that multiply to 16 and add to negative 8. However, it's actually also in the form of square double product square if you're really paying attention here. And so that should just end up being x minus 4 all squared. Either way, in the next line down, you can write it that way if you like. Now, the left-hand one, we can continue to factor the trinomial, leaving the 3 on the outside. X squared minus x minus 12 can also be factored. Make sure you know which one is positive and negative. We need two numbers that multiply to a negative 12 and add to a negative 1. The right-hand side, the right-hand expression can be written as x minus 5 over x minus 4 squared to save a little bit of room. But you just have to remember that that is equivalent to x minus 4 times x minus 4. All right, what do we need to have for a common denominator here? Look for the factors. So we've got an x plus 3, we've got x minus 4s, and we've also got just the number 3. So the lowest common denominator, or LCD here for short if we like, Well, we need to have the absolute maximum number of factors that either one of these expressions has. So the left-hand expression has a 3, the other one doesn't. It's going to need a 3. So when I say the maximum number, think about the maximum factors of 3 we need. It's 3. The x plus 3 factor, one of them has a single factor, the other one doesn't have any. The greatest number that we'll need here is x plus 3. So, any lower than one single factor of x plus 3 isn't going to be a common factor of the left-hand side, the left-hand expression. Now, the x minus 4, the left-hand expression has a single factor, the right-hand expression has 2 factors of it. The lowest common denominator is going to be the greater of those 2 values. We need to have 2 factors of x minus 4. And then we can start thinking about what pieces are missing. From the left-hand expression, we have 3, so that's great. We have an x plus 3, but we only have a single factor of x minus 4. So we're going to need to make sure to include a second factor, top and bottom. And the second expression is missing a lot of stuff. We're going to have to make sure we multiply that by 3, top and bottom. It does have the x minus 4 squared already, but it's missing an x plus 3. Now, by multiplying by the missing factors, we've achieved the lowest common denominator on both of these expressions. And now, the common denominator can be written out as one big fraction, and then we can add the numerators. Well, there we go. Now we've got one big mess. We've got one big fraction. The good news here is that we don't have 2 separate rational expressions. It's all combined together, but the next couple steps are probably best to complete on your own and see how you do. So now you might want to expand and then collect and then maybe try factoring to simplify. This might be a good time. You could try pausing the video and seeing how you do on your own. And I will write out the final result here in just a moment. And there we have it. I've expanded and collect. And I can try to factor to simplify, but it doesn't look like I'm going to get any common factors when I try this. The only thing that you might want to try factoring out is maybe a -1. And that's only so that if you prefer, you can factor out that -1 and put it out front as this one big negative sign. That will change the signs on the top to the opposite signs. And you'll end up maybe with something that's a little bit easier to look at, but you could just as easily leave it without factoring out the -1. All right, well, I hope that was fairly reasonable, but I'm trying to keep this video as short as possible. Definitely takes some practice. So we'll do more of these examples in class, and there'll be lots of them online for you to try as well. Anyway, I'll see you in the next video. Thanks for watching.